The purpose of this lab was to apply Newton's second law with the motion and forces of the spring and the energy principle in order to determine motion and energy changes of an oscillating spring. A pre-recorded video was uploaded to Tracker and its motion was analyzed and compared to a computational model created using VPython. It was determined that motion similar to that modeled in the video could correctly be modeled using VPython with changes in energy that satisfy the energy principle. This is the pre-recorded video used for the lab, which models a simplified version of the extreme sports rope example. Once this video was uploaded to Tracker, it was calibrated using the same specifications as those given in the Coursera videos. The distance from the point of attachment to the middle of the mast was set at 0.7 meters. The origin was set so that it was at the point of attachment with the positive x direction towards the right and the positive y direction up. The average position of the mast was tracked in each frame, and the data was collected in the graph and table to the right. In order to find specific values needed to initialize the code, certain calculations had to be done. Just like it was shown in the Week 10 videos, the period of oscillation can be found using the equation t equals 2 pi times the square root of m divided by k. I used that time that had passed after 3 oscillations in the x direction and found that the period of oscillation was 1.61 seconds. This was then used to find the spring constant, which was 6.123 newtons per meter. To find the relaxed length of the spring, the concept of static equilibrium was used. In static equilibrium, the system is at rest. Therefore, the net force is zero. Two forces are acting on the system at this time: the weight force downward and the spring force upward. The weight force needs to be equal to the spring force. By plugging in the known values, I determined that the relaxed length of the spring to be 0.057 meters. These calculated values were then used for the VPython code. The first initial conditions set were the mass given by the video at 0.402 kilograms. The initial position was found using Tracker at negative 0.109, negative 0.650 meters. Because the mass was released from rest, the initial velocity was 0.000 meters per second. The spring constant and the relaxed length were set at the values previously calculated. Then the code had to be adjusted to fit the calculation for L and S to be used in calculating the spring force. S is found by subtracting the length of the stretched or compressed spring and subtracting it by the relaxed length. The energy of the system was then found using the equations for kinetic energy, gravitational potential energy, and spring potential energy. The height used in the gravitational potential energy equation was the ball's position in the y direction because the gravitational force only works in the y direction. Then the while loop was set in order to include the weight force and the force of the spring, along with Newton's second law. After each iteration, the value for the energies change, and once they've been calculated, they become the initial values in the next iteration. The two forces shown were calculated using the same values for the force used in the calculation for the relaxed length of the springs. Newton's second law was used to update the spring's velocity and position. The value of S was then updated in order to account for the new position of the mass compared to the spring. Using the values that were set as K, U sub G, and U sub S initial at the beginning of the while loop, the changes in kinetic energy, gravitational potential energy, and spring potential energy were added. If I run the code, two masses can be seen in the simulation. The blue mass is the computational model, and the red mass is the actual movement of the mass in the video, which is uploaded into the code using a CSV file. The graph shows a change in energy, delta K represented by the blue line, delta U sub S represented by the red line, delta U sub G represented by the green line, and the total energy change represented by the yellow line. The first three show a sinusoidal pattern such as the movement of the mass, while the yellow line is constant. The model was fairly close in predicting the motion of the experimental data. The data in the x direction is more accurate, although the model motion moves slower. The motion predicted in the y direction moves faster and overpredicts the motion as it gets more negative and underpredicts it as it gets more positive. Differences could be accounted for not accurately tracking the average position of the mass. Also, the spring constant and the relaxed length may not have been exact for the spring used in this video. Therefore, the motion of the model would have been affected. The energy principle for the spring is satisfied. The total energy change is at a constant value of 0 in the graph. This is because work and heat are both 0 in the system. Therefore, total energy equals 0. As the kinetic energy of the system increases, the potential energy of the system decreases. As mentioned earlier, the period of oscillation in the x direction was found to be 1.61 seconds. The period of oscillation in the y direction was found to be 1.09 seconds. These values are slightly different, and that is due to the fact that the oscillation in the y direction is dependent upon the spring constant and how much it allows the spring to move up and down in the y direction. In the x direction, the motion is also dependent on the spring constant, but not as much as in the y direction. The x direction is also dependent on the angle and distance in which the mass was initially pulled back and released. In conclusion, it was determined that a computer model correctly determined the energy and motion of a spring mass system using VPython.